In this video, we'll discuss how the dimension of an eigenspace for a given eigenvalue of a matrix can be influenced by the multiplicity of that eigenvalue as a root to the characteristic equation. So in this example here, I see that a matrix A that it's upper triangular. It has diagonal entries 3 and 3 repeated twice and then 2. I have an entry here that I'm just leaving as a parameter, which I'm calling h, and all the other entries are 0. And the question I want to know is, how does the value of this parameter h affect the dimension of the eigenspaces? Well, let's just get stuck into it. A is upper triangular. Its eigenvalues are lambda equal to 3 and 2, but as we saw in the previous video here, because 3 is occurring twice along the diagonal, it's going to be an eigenvalue with multiplicity of 2. Let's just take the lambda equal to 2 case right away and get that eigenspace determined. So we look at A minus 2i. I'm going to subtract 2 along all the diagonal entries, and I'm not going to change any of the non-diagonal entries. I row reduce that. I already see a pivot here and here. It has nothing to do with the value of h. Whatever h is, I can ensure to use this pivot here to ensure that there's a 0 above. So it's going to row reduce to 1, 1, and then a column of zeros. Writing down the solutions here, you see x1 is 0, x2 is 0, and x3 is a free variable. So in vector form, we'll have x is equal to x3 times 0, 0, 1. So in fact, the null space of A minus 2i is just the span of this vector, and in fact it's one-dimensional. That had nothing to do with the value of h. To answer our question, h doesn't influence the dimension of the lambda equal to 2 eigenspace. It's one-dimensional, period. Let's now turn to the lambda equal to 3 case. This is where there's more flexibility, and it's going to be ultimately determined by the multiplicity here. So what we're going to do now is look at A minus 3i. I'll subtract 3 along all the diagonal entries. You can see how in this entry right here I now get a 0. That's significant. The non-diagonal entries don't change, and we now have this position here, h, that may or may not be a pivot. If h is not 0, that is a pivot position there. And if you row reduce this matrix, you'll get 0, 1, 0, 0, 1. Notice there was a non-zero entry here, but remember we'll always make sure to have a row of zeros at the bottom if need be. And so you write down your solutions to the homogeneous equation. x1 is now free, x2 is equal to 0, and x3 is equal to 0. So the null space of A will be the span of the vector 1, and that's our free variable in the first spot, and all the other variables are 0. You notice that the eigenspace is one-dimensional. Now let's look at the case when h is equal to 0. We now won't have a pivot in this position here. So we get a 0, 0, 0 along the top row, 0, 0, 0, and there'll be 0, 0, 1 here. After row reducing and getting things into the right position, I'll get a 1 in the pivot position in the third column there. Wow, look at what happens now. I actually have 2 free variables now because of that missing pivot from h being 0. I have x1 is free, x2 is free, and x3 must be equal to 0. So the null space is actually the span of the 2 vectors determined by the free variables 1, 0, 0, 0, 1, 0. And in fact, the null space is now 2-dimensional. So what's your conclusion here? The dimension of the null space is ultimately governed by the multiplicity of the eigenvalue. If the eigenvalue, like lambda equal to 2, has multiplicity 1, its eigenspace will be one-dimensional. But as the multiplicity goes up, it's possible for the eigenspace to achieve multiplicities anywhere between 1 and whatever the multiplicity is. In this case, for h not equal to 0, the eigenspace was one-dimensional. And in this case, h equal to 0, the eigenspace was 2-dimensional. That's because this was a multiplicity 2 eigenvalue. The most the eigenspace could be is 2-dimensional. But it could achieve a smaller dimensional space. It could be one-dimensional. So in the end, the multiplicity is the maximum dimension that the eigenspace could achieve.